Okay, so today we're actually going to review chapter 4, which is from stat 1. And chapter 4, we're looking at linear regression. And this is actually what we're going to study for the rest of the semester. So let's refresh our memories what linear regression is, and then we'll keep moving forward. So linear regression is an approach for modeling the relationship between a dependent variable, which is my y, and one or more independent variables. These are my x's. So in stat 1, we had just one x and one, well, I pointed the wrong thing, one x and one y. And if you notice here, I say one or more independent variables. So today we're going to look at just one x with the one y. But later on, we will get into the more, more than one, okay? So today we're going to review from stat 1, the simple linear regression. And this is what we cover in chapter 4. So I call this SLR, just abbreviate, you know, I do that often. So this is the case when we have one x variable. And I want you to keep in mind and just refresh your memory that x and y are numerical variables. So remember what we're looking at here with simple linear regression. We're looking at that relationship between two numerical variables, x and y. Okay. So as usual, we get to know our data and we do a few things. So we're going to start with that and just talk about and review what we do here with simple linear regression. We look at that relationship between x and y, our two numerical variables. Okay, so we have the variables and we need to know what these variables are, right? So we have our y variable. The y variable is what we call the response variable. This is the dependent variable. Then we have our x variable, and this is we call the predictor. It has a few names: predictor, the explanatory, the independent. Variable. And what we're looking at is where x predicts my y. So this is why y is the dependent, depends on x. X is independent. So we're talking about x predicts y. So when we're looking at which variable is the independent and which one is the dependent, we should always think about this. Okay, that X predicts Y. So the independent predicts the dependent variable. And when we look at these and think about them in this way, then a lot of times it's easy to pick out which one is my X and which one is my Y, if it's not given to us. Okay. So those are my variables that we're going to be studying here today. And we have a graph, right? We can view. So the graph that we can look at here is the scatter plot. So we learned about a scatter plot in Stat 1, and this is just a graph of each XY pair. It displays the relationship between my X and Y. So it's a graph of all these XY pairs, and it gives me an idea, just a visual of the relationship that's going on between X and Y, right? So we have a few things we can look at and we can do. So when we're looking at a scatter plot, we can describe that strength and direction. So if we're going to describe the scatter plot, we talk about the strength and direction. So what I'm talking about here, is it strong? So is it a strong relationship? Is it moderate? Or is it a weak relationship? We're also looking at, is it positive or negative? This is where we're looking at the slope of the line, positive or negative slope, okay? So here, when we have a scatter plot, something like this, okay? This is my X, this is my Y. This is going to be a positive. You can see the line would go right here, okay? So this would be a positive slope to my line. So that's how I can tell that direction. Or if we had something just in the opposite direction, like this, here we would see that we have a negative line. So there's my direction, okay? So when we're looking at these, we could also use R, or lowercase r. We can use, use R here. And there's a lot of examples in our type notes starting at page 2 of these scatter plots. Feel free to look at those if you would like. But I want to talk about R next. And I want you to remember that R measures exactly what we're talking about here, the strength and the direction of our relationship. So my scatter plot gives me a visual, okay? And we can say, well, how strong or weak the relationship is based on how close the lines form a straight line and the direction. Okay, so the direction of the line, if the slope of the line is positive or if it's negative there. But R is a numerical value that describes that. So let's talk about that because we can a lot of times use R with our scatter plot together. And then that way we have a measurement and a visual. So this is called my correlation value. and this is R, and this measures the strength of the linear relationship between X and Y. The key word here is linear, right? This is the key word. So my correlation value is R, that's my notation R, and it measures the strength. So it tells me how strong the connection is between X and Y. So how close these dots are to forming a straight line, right? So that's what R tells me, that measure of strength, but for a linear relationship. So it tells me how close they are to forming a straight line, not a curved line. So this R is only for a linear relationship. So if R is not a strong number, which I'll give you the scale here in a minute, it doesn't mean that there's not a strong relationship. It just means there's not a strong linear relationship. So the word linear here is key for us. Okay. So let's take a look at what R could be. So R is between -1 and +1. So if we have this scale, -1 up to +1, 0 is right in the middle, right? So here, if our scale kind of, let me just put some values in here, -0.4 and +0.4, +0.8 and -0.8, like this, okay? So anything here in this section where it starts at -1 and goes to -0.8, or 0.8 in the positive side up to 1, those sections there in R value between those numbers are considered strong. So this is a strong relationship. Now, the sign, negative versus positive, tells me the direction of my slope of my line. So negative direction or a positive direction, okay? Then we have anything here in between the -0.8 to -0.4 or 0.4 to 0.8. This is what we call a moderate strength. Then anything in between here, okay, -0.4 up to +0.4, we consider this weak. So anything close to 0 is considered weak, but I'm talking about a linear relationship. So if I have R equal to 0, this just means that there is no linear relationship. It doesn't mean that there's not a relationship at all. It just means there's no linear relationship, okay? So there could be a curved relationship. It could look like a parabola, right? And that could be a relationship. It just wouldn't be a linear, it wouldn't be a straight line. That's all we're looking at. Or if we have an R that is equal to +1 or -1 here, then this is what we consider a perfect linear relationship. And here we would look at our points making a perfect straight line. Remember, negative would mean that my slope of my line is in the negative direction, or a +1 would indicate that my slope of my line is in a positive direction. So there's the direction piece for the R, okay? So here, I want you to know also in the type notes on page 4, you can find more information about our correlation value, and you can see this scale there as well. Okay. So when we're looking at these, we interpret the scatter plot in the R value by just making a statement about the direction and the strength of our linear relationship. So when we're looking at our regression here, if I can pull this back up, we're looking at simple linear regression. So that's what we're interested in, the linear relationship, okay? Not a nonlinear relationship. So here, to interpret the scatter plot, squeeze it in here. I'm going to say and R value. We want to talk about the strength and direction of our linear relationship. So you could say something like, there appears to be a, and then you're going to talk about the strength, and then you will talk about the direction. I'll fill those in a second. Linear relationship. Between your X and your Y variable. You don't just say X and Y, right? You put it into context. Let me just fill these in here. It doesn't matter if you talk about the strength first or the direction first, does not matter. It doesn't matter if you talk about the Y variable and then the X or the X and the Y, it does not matter. Just filling it in. Okay. And you don't have to use a statement. You can write it any way you want, right? It's just you want to make sure you put it in context. So what the problem's about, and talk about that strength in the direction. And make sure you say it's a linear relationship because that's exactly what it is, right? Okay, so this is all the stuff that we do before we actually build our model. And when we build our model, we actually call it perform regression analysis. So when I say we're going to perform regression analysis, you're just going to build your model. So you're going to build your model with the getting your line of best fit, right? Your least squares regression line, just like what we did with in step one. Okay. So my least squares regression line. This is what we call the line of best fit. Okay, and this is where we get the regression equation. So think back to step one, since that's what we're doing, we're reviewing. We took our XY and yes, we looked at a scatter plot, we looked at R, but then we also got our least squares regression line. So it's the line of best fit. It's the line that best describes that X and Y relationship, okay? And so we're still gonna do that here. It's just, of course, we're gonna have Minitab do all of this for us, right? So I need to give you some more information about this line of best fit. So we have, now this is going to be a little part of new for us, okay? So we have our equation for the population. See, we didn't do this in step one. We didn't talk about our equation for our population, okay? Our equation for our population is yi is equal to beta 1 xi plus beta naught plus, this one's new, epsilon I. I will tell you what all of these are because it kind of looks like a lot. So I'll write it over here. So beta 1, write it out here. We all know beta 1, the 1 there. This is what we consider a population slope. Okay. And then we have our beta naught. And this is our population y-intercept. Then we have this epsilon. This is what we call our random error term. This is the residuals. That's all this is, my error, right? It's the residuals here. So if we think back to step 1, we actually used an estimate equation using the sample, and that's what we did. So here we have our estimate equation using the sample. And this is going to look familiar from stat 1. So our estimate equation, here in stat 2, we're going to use y hat is equal to b1x plus b naught. But in stat 1, we used y hat equals ax plus b. So this should look familiar. And in algebra, we used y equals mx plus b. All I want you guys to know, it does not matter how you view your equation of your line. The number in front of x is always your slope, right? So it doesn't matter if we use an a in front of x. It's the slope of my line. It doesn't matter if we use m like we do in algebra. It's the slope of my line. So here, it doesn't matter if we use b1, right? It's still just the slope of my line. So it shouldn't matter when we're looking at an equation of a line, it shouldn't matter what symbol or notation we use for the slope. We know it's the number in front of x, right? And when we're adding or subtracting another number, we should know that is our y-intercept. Okay? So we may not even see it in this order, right? We could see our equation of our line y hat equals b naught plus b1x, right? And the order shouldn't matter. We just know that b1 is the number in front of x, and that is my slope. Okay? So we just want to keep that in mind. We want to be a little bit flexible about that. We don't want to be rigid and say we have to see it in this one way all the time. The order might change, right? Our notation might change like it is here today, and it's okay. It still means the same thing. I want to talk about these residuals, right? Epsilon, this is from my population. You know, here we're using our sample to estimate. So this is what we're going to see. But let's talk a little bit about this epsilon, this error term, the residuals, and where this looks, where this comes from, like what this looks like here. So let's take a look. Okay. So for our residuals, I'm going to give you a visual because I think the visual is the best way to go here with this. So if we have a scatter plot, this is my x, this is my y, okay? And we're looking at, let me put some points here. We have a scatter plot that looks something like this, okay? put a couple further out. There we go. Okay. And if we get our line of best fit, that would go somewhere. I feel like I need a ruler. Go somewhere right up the middle. I don't really have one. Let me see here. I don't have one on hand, I should say. Let me use the other paper. And that's at least semi straight. Oops, I went away from the paper. Okay, there we go. Say that's the line of best fit, okay? I don't have the equation for it, but that's what it looks like. There we go. Okay. So what we're looking at is if we take some X value, maybe this one right here, right? Maybe I'm gonna look at this one right here. And this is XI, okay? So when we look at this over here for Y, that's YI. So this point right here is XI, YI. It's just one of my points, right? So what I'm looking at, and I'm going to zoom in because I want you to be able to see this. What we're looking at is this distance from the point to the line. So this distance from the line and the point here, that's my residual. That's the error, right? Because my line is saying one thing, but my actual data point is saying something else. So this right here, try to line this up as best as I can. That right there, that distance is my residual, my error. Okay, so there's the residual of the error. And what we're looking at is some Y value over here. So for this same XI, I have an actual data value of YI, but I have a predicted, what my line is predicting would be the Y, would be over here, Y, and we call this Y hat. Y hat is what we call the predicted. And we have an I here, okay? So what we're looking at is the residual, the calculation, of course, equals Y minus Y hat. So this distance between these two, Y and Y hat, the distance between these two from the point to the line is Y minus Y hat. So it's actual minus predicted. Y hat is predicted and Y is an actual. Sorry, I'm off the paper because I'm zoomed in so far. Okay. So I just like to give you guys just this visual because I think it's so helpful. And I'm going to say this again. I say it in step one. I want you to remember that this line will always pass through the point of my sample means. So X bar, Y bar. Okay. So that's my residuals. It's my error. Okay, so when we're looking at our equation of our line, pull this back up right here. If we're looking at our equation of our line, so we have our Y hat equals B1X plus B naught. Okay. We can interpret and talk about a few things from our equation of our line. Hang on, I gotta straighten this out because it's driving me crazy. It's really crooked here. Here we go. It's a little bit better. Okay, so the first thing we can do is we can interpret the slope of the line. So this is all under what we call the regression analysis. So a regression analysis will give us our equation of our line. And from that, we can interpret the slope of the line. So what we're talking about is we're interpreting what this B1 value is. So all this is for each unit increase in my X variable. So that predictor variable, the Y or response variable is either going to increase or decrease. Now that's the slope of my line, or the direction of the slope, by the slope. This is the positive slope, this is the negative slope, and then here is by the slope. We can say on average to be correct. So I will put that on average. Okay, so now this is the interpretation of the slope of my line, and you don't have to say exactly what I say. I'm just giving you an idea. So for every unit increase, so I'm normally pretty specific. Like if we're talking about temperature, and we're talking about degrees, then I'll say for each degree increase in temperature, my slope my Y will increase or decrease. So this all depends on the slope on this value. So if it's a positive number, then it's going to increase. If it's a negative number, it will decrease by this amount. So what I'm saying is Y is directly related to X, right? So for every X increase, my Y will increase or decrease by this number. And that's what we're saying. So we're just interpreting the slope. We're just putting it into words. Okay. And then we can also interpret the y-intercept sometimes. We don't do this all of the time, and I will tell you when we won't do this. So this one's pretty simple as well. So when my X or predictor is 0, the Y or response variable is the y-intercept. After all, that's what it is, right? So if you were to plug 0 into your equation here, you plug 0 in here, then my Y value is my y-intercept. And that's all we're saying. Okay, so if the equation of if my X is 0, then my Y is equal to my y-intercept. So that's all we're saying. It's pretty obvious. It's not anything crazy or different than what we would have done in algebra class or even in Stat 1 there. So, but we do have two situations where we won't do this, okay? So let me just write this. We will not interpret the y-intercept. And we have two reasons where we will not. So one, if X equals 0 does not make sense for the data or context. So if we're talking about our X being height, someone being 0 inches tall does not make sense. So I'm going to put over here context either. It's not necessarily just the data, it's the context, like what we're actually talking about, right? So then we're not going to interpret a y-intercept because that would be X equals 0 and it doesn't make sense. So it would be one scenario. The other scenario where we're not going to interpret this y-intercept is when we already have a value from our collected data that's close to X equals 0. So if we already have a data value at or close to x equals 0, then you're not going to interpret. So if you have, let's take a look at our scatter plot. If we have a point that's pretty close to my y-intercept right here, I'm not going to interpret where my line would say, my y-intercept from my line, which would be down here, if you follow that, when I already have a data value up here. So we don't do it in that case. Okay, so those are the two scenarios when we won't interpret that y-intercept. Okay, so when we get this line of equation, this equation of our best fit or line of best fit, we can use that equation. We can use it in two different ways. So we saw here in our scatter plot, we can predict, right? So we can predict in two ways. So I can predict using my graph here, okay? Just by going up and then over. So up to the line and then over to the y-axis. So I can predict that way, or I can predict by using my equation. So I don't actually have to do this by hand anymore. Minitab will do this for me. So of course you could always do it by hand if you would like, but it's not necessary. So we just call this make a prediction. Or estimate. Okay. So we're going to use that y hat equals b1 x plus b naught. Okay. And Minitab will do this for us. Okay, so we can make that prediction. So if we want to know for a certain value of x what that y would be based on our equation of our line, we can just ask Minitab to do that for us. Okay, and I will show you in an example how to do that. It's like towards the end of the example, but we can look at doing that. Then we have another value that we're interested in, and this is called my r squared. So r squared, this is, let me just also write lowercase r squared. This is the coefficient of determination. So my coefficient of determination, this determines how well the line fits the data. So r squared, which can be either one. So lowercase r squared is actually my lowercase r being squared. The notation on Minitab is uppercase r squared. It's just remember lowercase r squared is when we're using that least squares regression line. There's other ways of calculating r squared, but what we do is we use the least squares regression line. So it's actually lowercase r squared, but the notation is still uppercase r squared. If that makes sense to you, it's all the same thing. So this is the proportion or the percentage of variation in that y variable. So that's my response. That is being explained by the line. So this is the proportion that does a good job explaining the spread. Okay, so that's what r squared represents. It's the proportion that does a good job explaining the spread, that variation of our y variable. Okay. And the error, the residuals, is what's not explained. So this is what is explained, my R squared. My error is what's not being explained by that line, that variation, okay? The higher the R squared value, the more useful the model is. So now we're looking at this, where R squared is telling me how useful my model is. And making those predictions or estimates. So R squared is not only telling me that proportion of variation of my Y that's being explained by the line, but it's also telling me how useful my line is for making predictions or estimates, okay? So here we're going to use R squared, sorry, I wanted to use capital R. Capital R squared is greater than or equal to 75% as a good fit, okay? So we're going to use that. And we're going to use this loosely. And what I mean by that is if we find R squared to be like 74%, I would say that's close enough to 75 to be a good fit. It's not a hard 75 where you're saying, oh, it definitely has to be greater than or equal to 75 for sure. We're just saying loosely, around 75% would be considered a good fit, meaning that my line is useful in making predictions or estimates, okay? So we just use that loosely from our model. And again, we can get this R squared. We can calculate it by taking R and squaring it, or I'll show you where we can get this value from our Minitab output when we're looking at our regression analysis. We have our standard error. Of the regression model. The notation for this looks like S in Minitab. But you know we use SE, right, for standard error, okay? So I just want you to know Minitab uses S, but it's still what we consider SE for our standard error, okay? So our standard error for our regression model, this is our estimate for the standard deviation. This is in the same unit as the response variable. Which is my Y variable. And what this tells me, it's the typical deviation from the regression line, okay? So this is calculated from the error part that is not explained by the line. And this is SE equals the square root of MSE. I'm just giving you this, but we're going to do this later. I want you to know. We will look at this later. Not today. We're going to look at this later on. Okay. So the standard error, it just estimates my standard deviation. That's what standard error always does for us. It's the same units as my Y variable, and it's just telling me exactly what standard deviation tells me, that typical deviation from the regression line, right? And it's calculated using that error, okay? The part that's not explained by the line, okay? I'm going to mention one other thing that we might see, and it's fine if you guys want to use this, and this is called the fitted line plot. Once in a while, I pull this up. And the fitted line plot is just the scatter plot with the line on it, okay? I like to mention this because a lot of people will ask me about this. They'll see it and they'll pull it up, or they'll just see it someplace else, so I like to mention it. So it's my scatter plot with the regression line included. So I like just to mention that, okay? So we might see that, fitted line plot. Okay, so when we're looking at this model, of course, we have requirements, right? So we always have requirements that tell us if our model is a good model, right? So here are requirements. We have several requirements. I'm going to quickly go over them, and then we're going to talk more about them next class, but I want to quickly mention them this class. These requirements will tell us if our model is valid. So if it's a good model to use. Okay. So these must be met. So the linear model is valid. So if you don't meet a requirement, then you say the model's not valid, or the linear model's not valid, okay? So I actually have separate notes typed up, and these are called the residual analysis notes. So they're not in our regular type notes, separate. So residual analysis, this is called, okay? So I want you to recall and think about that population line I gave you. And I want you to think about epsilon here. So requirements is based on the epsilon. That's our error term, okay? All right, so I'm going to quickly go over these 4 things. And like I said, we will talk about them and look at them a little bit on today's daily, but we're going to really do more with them next class, okay? So the first requirement that the residuals must be independent. So what I'm looking at here is no pattern. I'm looking for no pattern. On what we're going to get, the residuals versus fitted plot. Okay. Our second requirement that the residuals must have constant spread. So that's my variability. Okay. So we're talking about the residuals must have constant spread or constant variability. And here we're just looking for them to be pretty straight across. And we'll look at some visuals, like I said, next class, and we'll kind of talk about this a little bit. I'm wondering if I have an example in my notes. I'm not sure. I got to think about if I do or not on this. I mean, I know I have an example in the notes, but I'm wondering if I have an example to walk through. Okay. I'll check that out in a minute. Okay, so my third requirement is no outliers. And what we're saying here with no outliers, we're looking to have them within 3 standard residuals. And our fourth one is that the residuals should follow a normal model. So that's not new for us, following this normal model. So here we're going to study an NPP and the p-value, right? What we're looking for is that p-value to be greater than 0.05 to go ahead and assume normality, right? And that's what we're going to look at. So let me see if I have any of these. Well, I'll look at them in just a second. I think I have it part of my example, but we'll look at it in just a second. But these are my requirements that need to be met. So if one of them is not true, then we would say our model is not valid. Okay. These don't take a real long time. And today on today's daily, I give you the graphs and you're just going to look at them. So for part 1, we're looking to be independent. So we're looking for no pattern. Okay. So we don't really want them to follow some kind of curve pattern or anything. We just want them all over the place. And the same thing with number 2, you really want them all over the place. So we want to stay away from what we call like a sideways V here. So you don't want like the spread to be, small in one section and then big in another section. You want it pretty the same. So if they're all close to the middle line, then you want them to be all close to the middle line. You don't want it to be up and down. And we'll look at this more. So it's okay. It's okay. This is like just the first day of this. And then no outliers. Outliers. We want to stay within 3 standard residuals. You'll see on the plot where +3, -3 is. You want them in between those 2. And so that's an easy visual. And then here, just our NPP p-value greater than 0.05. So that's not new. I want to take a look at an example with you guys. I know I'm taking a long time here. So let's take a look real quick at example 1 on page 10 of the regular typed notes. And we'll go through this. I'm not going to spend a ton of time on like the old stuff. We'll just quickly go through that, but I want you to look at the new stuff and the mini tab. So let's take a look at these notes. So it's day 21, which is so crazy to me. Day 21 notes on page 10. Okay, so here we're looking at birth weights of babies with adolescent female mothers. Okay, so here we have our data. So we have mother's age. You can see they're all teens, right? Adolescent females. And then the baby's weight here, okay? And it's in grams. It's not in pounds, in case anyone was wondering. If it was pounds, it'd be a problem. So when it says to get to know the data by addressing the following questions, it's just picking out all the information, okay? So what is my response variable? So we want to know X predicts Y. So always keep that in mind. So I want to know if mother's age is going to predict the baby weight, right? So the baby weight's my response variable, and the mother's age is going to be my predictor variable. Does that make sense to everyone? You can kind of see that sometimes you can go either way with something, and it's really necessary for me to tell you which one my X and which one's my Y. Okay. So, and don't hesitate to ask either on that. So here it says use Minitab to get a scatter plot. Okay. Then we're going to use Minitab to get our correlation value, that's R. And we're going to study the scatter plot and the correlation value to make a sentence of interpretation. So that's the direction and the strength of my linear relationship. Then it says use Minitab to perform regression analysis. Regression analysis is just getting my equation of my line. Okay, that's all that is. So, and then it says right here, paste the regression equation output here. Now it says assuming y equals ax plus b, a plus bx, sorry, provide an interpretation of the predictor. So my coefficient b and the y-intercept a. So all it's saying is interpret the slope and the y-intercept. Then using the model summary, identify the standard error. So it's just S, it's just picking out some information. Okay, so let's go ahead and do that stuff first. So we have this data under day 21, it's called the baby weight data. I already have mine pulled up, so I'm going to share that and we'll take a look at the Minitab together. Okay, so here's my Minitab. So we can see we have two columns, one column with an X and the other column with a Y. Sometimes it's easy to rename these. So remember the baby weight is the Y, the response. Oops, I arrowed over too far. So you can rename it. You could say response Y if you want in there. If you want to rename mother's age as X, because what's nice is then you don't have to keep guessing which one's which. Predictor or explanatory X, right? So this way, when I'm building my model, when I'm doing everything, I'm not guessing which one's X and which one's Y again, okay? And that's why we identified that early on. All right, let's take a look at that scatter plot. So a scatter plot's just up here in graph, and it's the very first option, scatter plot. I'm just gonna click on that. So here, we're just going to do a simple scatter plot. We're not going to do anything with groups. Right here, you can see with regression, that would just be my fitted line plot. I'm just going to do a simple plot right here. So that's already chosen, and then click OK. And then right here, it says, what's my Y variable and what's my X variable? So my Y variable, like I renamed, is the baby weight. X variable is mother's age. Okay. I could just go ahead and click OK. If you want to play around with any of these options, feel free to do so, but you don't need to do anything there. So I'm just going to click OK. So we click OK, we can get an idea of a scatter plot. I can see the slope of that line is positive, so that's the direction. The strength looks like moderately strong to me, okay? It's not real weak, it's not all over the place, but it's not a straight line, so it's not super strong. I would call this moderately strong, just by a visual, okay? So there's all my output. It's a pretty nice graph. It gives you a nice idea of what's going on. So now it says, let's go ahead and get our value R. So this is our correlation value. So I'm going to go under stat, basic statistics, and all the way towards the bottom, it says correlation. Oops, I did not mean to click on that already. So let's go back, stat, basic, correlation. Okay. So when I click on correlation, it will ask me for my X and Y again here. So I'm going to go ahead and enter them in. I'm going to put my X in first and then my Y in second. It will give you the same number if you put it the other way around. I'm going to put X in first and then my Y in second. And I don't really have to click on anything, but again, you could kind of play around with results and graphs and options if you want. And look at what happens. It gives me a graph again, and then here's an R right here in the bottom of my graph. Right there, 0.884. And then look, I'm going to go down a bit further, and here's my correlation. Here's that 0.884. So I have it in two different places here. the reason why I put my X in first and my Y in second is when I get this graph, it gives me my X and my Y in the correct location. Okay, Minitab doesn't know which one's X, which one's Y. So by putting the predictor variable in first, I'm telling it that's the X. Your correlation value, if you put Y in first, will be the same, 0.884. It's fine. But your graph would be backwards. I'm just throwing that out there so you guys are familiar with that. So I always put in my X first and my Y second. Okay, and here's the output. So if I'm asking for the output, this is what I'm looking for, this 0.884. So that is pretty strong, right? 0.884 is pretty strong. So I said more of a moderately strong, but now looking at the actual R value, I'm going to say it's a strong positive linear relationship between mother's age and baby's weight, right there. Okay, so there's my interpretation. So now let's go ahead and fit our model, or I don't really want to say fit our model, but perform regression analysis. You'll see where it is calling fit the model. So I'm going to look back at stat, and you're going to notice the second option down is regression. So we're going to go right there, stat regression. Look at the very first option. It says fitted line plot. So there it is again. So you can get that fitted line plot like we discussed in class. But we're not going to go there. We're going to look at regression. So stat, regression, regression again. You guys know all these steps are in the typed notes, right? I'm going to fit my regression model. It's the very top one here. Okay, so I'm going to fit my model. I'm going to click on that. So all this does is it tells Minitab, it's just like the ANOVA. It tells Minitab what column holds what data. So my response is my Y, so that's the baby weight column. And then my predictor is my X, right? That's column 2. I am not using this bottom box, just these top 2 right now, okay? Okay, so we can go ahead and play with other things if we want. We don't need to. So I always tell you, like, if we need to, right, we'll click on certain things. Here, we don't need to right now. So right now, I'm just going to click OK and then move on. So right here, this output, just slowly scrolling through this, okay? So this output kind of looks familiar, doesn't it? Looks really similar to what we saw in our ANOVA output. Okay, so I want you guys to just be aware of that. It looks fairly similar. But right here on the top, the regression equation, this is what I'm looking for. So when I say perform regression analysis, this is what I want. I don't need the whole thing. I need this. I want my equation. Okay. Just remember, whatever your column headers are, that's what comes into your equation, right? So that's what's right there. And then look at down here, my model summary. In my model summary, here's S. That's my standard error. Okay, 205.308. Here's my R squared, 78.09. This would be my lowercase r squared. We don't use these other 2 yet. Okay, so for today, we're just using this R squared, that's 78.09. Okay, later on, we'll use the next one over, but not today, not right now. Okay, so that's performing my regression analysis and picking out the information. Okay, so if we wanted to do a fitted line plot, we could go back into stat regression and fitted line plot. I just want to show you guys. My response, of course, is Y, predictor is X. You could see a lot of this comes in linear. We're going to leave this on linear and then click OK. So here you can see, look at, I have all the same information. So a lot of places, you can go different places to get the same information. Here's my equation of my line. Here's S, here's R squared, right? And you go down here and here's your scatter plot with your line. So you can see all of that there. So it's nice. You can go a lot of different places and get really the same information. So that's really nice to see. So my R squared is 78.1 or 78.09. So that's greater than the 75%. So we would say that the model is a pretty good fit, right? So the model is useful. That's what we say. It's useful for predicting values of Y given values of X. That's what we're looking at. Okay. Now let's take a look at predicting. I'm not going to go back to the directions, but the directions say it wants you to predict a baby's weight based on a mother's age being 18. Okay, so it wants me to use this equation. Yes, I can do it, this equation or this line. I can just plug in x equals 18 and calculate it, right, by hand. It wouldn't take very long. You could use the graph, and that's not very specific, right? So really the calculation would be the best, or I'm going to show you how to do it on Minitab. So if you go into Minitab, you're going to go back to stat and back to regression, okay? And I'm going to go back over one more time to regression again and look at the third option down, says predict. Now, this is grayed out before you fit your model. So meaning you have to tell Minitab what your model's about. So which column has your X, which column has your Y, and actually make your model first before you can predict anything, right? Because otherwise it doesn't know what equation to use. So I fit my model already. I did my regression analysis. So now I can go ahead and predict. So you click on predict. So everything should fill in for you. You shouldn't have to really change much, but I just verify. Response, yes, is baby weight. And then here I'm just going to enter individual values. The other option is a column. So like if I already made like another column in my spreadsheet with a whole bunch of values, I don't have that. I just want to add some individual values. You can add them right in here individually. All we're looking at is 18. So we're just saying when X is 18, I want to know what Y is. I don't have to do anything extra here. I could just go ahead and click OK and get an answer. So right here, you have all this output and it's kind of hard to tell, well, where is my answer? My answer is called fit. So you want to look right here for the answer, which is fit. So it's 3,249 grams, okay? That is my prediction based on my equation, okay? My line of best fit. And then you know what? The last question says, what about predicting for a mother that's 38? Well, you have to think and make sure that what you're predicting is in the scope or the range of your data, right? So what we're talking about is adolescent mothers, so teenagers. We're not talking about 38-year-olds, right? So someone that's 38 is not a teenager, not adolescent. So I would not predict a baby's weight based on a mother's age for this model for a mother that's 38 years old. And that's what you would say. So you would just say it's not in the scope of the range of the data. We cannot predict for this because it's not what we're really studying. Okay. All right, let's see here. I want to just show you really quick, and I know we're kind of running low on time. The residual analysis, I just want to show you what we're looking at. So this is what your plot's going to look like here for our residuals. You're not going to be asked to get the plot. We'll do that later on, meaning another day. So you just see how this plot is all over the place. That's a good thing. Okay, so there's no pattern. I don't see a pattern. Okay, some of them have a certain pattern, like this one has a pattern. So that would not be good. So independent means no pattern. They're all over the place. That's a good thing. And then what we're looking at for the constant spread, the constant variability is like this. So all of them are pretty, like it's pretty constant from left to right or right to left, that how far they are, right? You've got some dots close, some dots far, right? Something that is not a constant spread, I hope I have an example right here. See this one over here on the left? Look over here on the left. It's the spread is a lot closer to this middle line and then it gets further apart. So that's not a constant spread, right? The spread's smaller here on the left and then larger on the right. So that's what we call our sideways V. You want to look for that. You do not want a sideways V. All right, a sideways V is not a good thing. So these are what you do not want. So look at this one on the right. So you have a larger variability, larger spread on the left, and then it goes down and gets closer to that middle line of 0. on the right. You do not want that. So that's what I'm talking about when I am asking about a constant spread. So you want them to be all over the place and pretty constant when you're looking for that. Okay, so I just wanted to show you guys that. I give you the plot on today's daily, and then I just ask you